formation organs. Here we use a sample. And a sample that way the porous stone. Porous stone here also called permeable stone to ensure the drainage. Okay, and we should measure the compression, the vertical compression through the dial indicator on the top of the crane rack. Okay. We apply load and measure the compression. Use this equipment. Here's water container. Here's a cutting ring. We use cutting ring to take the soil sample. Okay, and the inner rigid ring outside the cutting ring. Maybe the inner rigid ring. The function of inner rigid ring to confine the soil sample. Okay, so we can call confined ring. Here the red color indicate the inner rigid ring. Okay, when we apply load, the poor water will be cut from the void. The poor water will escape from the void. So the poor water enter the water container. Okay, and the sediment will occur, and we use the dial indicator to match the sediment, okay, the compression. Here's two methods, one for low speed, another for high speed. If the soil sample is a sand sample, we can use high speed test. If the soil sample is clay sample, then we use low speed test. Okay, maybe the consolidation costs more time. And the incremental loading from 15 to 100, 200, 300, and 400. Apply load instead. Okay, first 15, and then increase to the load 100 and 200, 300, 400. Okay, and when the load applied, the sediment will increase. When the sediment can increase no more, reach the maximum value, the sediment can increase again, reach the maximum value. We use these values for analysis. Okay, that's for the segment. When we measure the compression data edge, data edge due to the void value decrease. So that will give a relationship between the data edge and the void ratio. Okay, what's the relationship between the compression and the void ratio? That will give the relationship. From this figure, maybe the left indicate the source sample before compression, and the right figures indicate the source sample after compression. Okay, before compression, the initial head H0, okay, and have a section area, same section area when the compression occurs. Maybe the section area not change, only the head change. Okay, section area is constant. So the initial head equal H0, and the value of void equal E0. Okay, and the value of source particle we assume it 1 unit. Okay, so the Vs can raised by the H0 divided by E plus E0. Okay, because the section area is a constant, so the value ratio equal the head ratio. Okay, maybe the value of source particle. Use this equation. And after compression, when we apply node to the source sample, and a settlement occurs, or compression occurs. So the head of the source sample changing the H0 minus FH. Okay, that's for the head after compression. And in this condition, the void ratio changing. Okay, maybe the void ratio decrease. Okay, maybe decrease due to the compression, and after compression, the void ratio will use E, and Vs use 1 unit. For these conditions, the value of source particle can use this equation. Okay, in this condition. So the source particle value will not change before compression and after compression. In the process of compression, the soil particle value can change. So we can get this equation. Before compression, the value of soil particle will use H0 divided by 1 plus E0. Okay? And after compression, we use H0 minus H divided by 1. Okay? So, use this equation, we can derive the compression or segment, or we can derive the watt ratio. Okay, the first equation can this. Okay, that's for the compression segment of the soil sample, and we can use the equation for the watt ratio after compression. Okay. If we measure the initial watt ratio, how to calculate the initial watt ratio? In the soil physical property, we derive this equation. Okay, use the three-phase figure. We can derive this equation. Use this equation and the unit weight of soil particle and the water content and the density of soil particle, density of water, and water content is given now from the laboratory text. Okay, so we can derive the initial watt ratio. And next, we use the watt ratio and know the relationship of watt ratio and know to indicate the soil compressibility. Here's EP curve. We call EP curve. Here, the node increase with time. Okay, we use the node state 15 or 100, 200, 300, 400 for the node. Okay, and then the segment will increase to segment 1, segment 2, segment 3. Indicate the maximum segment for each state node. Okay, and we should use the Watt ratio. Maybe the Watt ratio will decrease to decrease Watt ratio 1, Watt ratio 2, and Watt ratio 3. Okay, and this this three Watt ratio can calculate it by this equation. Okay, so we can have these figures here for the node and this for the Watt ratio and the EP curve like this will decrease. The Watt ratio decrease with the node. Okay, but for various kind of source, maybe the curve is different. Some source have a EP curve like this, and for another kind of source, maybe have a EP curve or for some deep source, maybe EP curve like the blue color lines. Okay, so the EP curve, the step of the curve indicate the compressibility of the source. Okay, if the slope is deep,